All right, so when we decided to divide up the work for today in terms of figuring out ASR, I decided to dust off. This is actually a talk that I gave 4 years ago here, and it's been updated and modified a little bit. And unfortunately, John is going to have to suffer through it again because it actually comes directly out of my class slides for my spoken language processing class, which he just sat through. So, you don't get to ask any questions. But everybody else, no, I'm kidding, John. But everybody else, I want to hear. You're too dead today, so feel free to jump in, and you guys should feel free to jump in as well. As I'm sure you will, because I know Sanjeev. Yeah, no, right. Well, that's why I have the stick, Sanjeev. Okay. Right. Okay. So, Dimitra just gave you a nice introduction to the basic ASR principles. I'm going to show you how to look at it a slightly different way, but it's really the same stuff that we're looking at, and by using finite state machines. And I'm going to give you an introduction to finite state machines, and then how they relate to automatic speech recognition. I'm going to hit myself on this. So in the afternoon, there's a lab, and we debated for a while whether to do this using the FSM tools, which I did in 2004. And we decided, no, we're going to actually use HTK there. But if you're interested, I have the stuff both from my class and from the 2004 workshop that people can play with. And I'll give you my email address at the end so you can send me email if you're interested in playing around with this stuff. OK, but don't fall asleep. Don't say, oh, this is all worthless because we're not going to use it this afternoon, right? Because actually, the same underlying technology is going to be used in the term detection stuff. So part of the reason why I'm doing this today with the FSM is actually in service of Richard Sproat's group's presentation on term detection, because they use this stuff a lot too. So same underlying things. OK, so how many of you have done finite state automata to death? OK, only about half of you. OK, all right. So let me give you a quick introduction, and then this is something that you see the beginnings of in most computer science curricula, but we'll take it sort of one step further. So hang in there if you're like, oh, automata again. All right. OK, so first of all, what is a finite state machine? It's a machine that accepts a regular language, and the basic definition of that is something that isn't context free. So a number of A's followed by a number of B's where n is not necessarily equal to m, no restriction on n, but not a number of A's and followed by a number of B's where they have to match. Right? That's the basic definition. If you want to match, then basically you have a context free grammar. Now you can actually use this finite state technology to do a recursive version of a context-free grammar that goes up to a limited number of n. Okay, and we do that for parsing, for example, in one example of something that I've done before. So what we're going to do is we're going to have a bunch of states, and we're going to have labeled transitions. So this is slightly different than the model that Dimitra was showing you earlier, in the sense of when she was showing you HMMs, she had HMMs that where you had states, and the states emitted symbols. Okay, here we're going to have symbol emissions on transitions. Okay, turns out the two are equivalent. Don't have to worry about one or the other. We could go through formal, if we really want to do it, go through the formal proof of that. We don't have to do that. Okay, but the idea is we might label states with a name, but that's just sort of a conceptual name. Symbols will be emitted on arcs. Okay. So there are two types of machines that we're going to talk about today. One is basic automata, okay, and that's the stuff that you might have seen before. And then transducers, which you might also have seen before, but basically talk about pairs of symbols, inputs and outputs. Okay. So a finite state automata basically gives constraints about the language that you're working in. So the idea is that if you can find a path through this graph, then that corresponds to a sequence of labels in your language, right? Then that language is accepted by, that string is accepted by this language, okay? So what we're going to do is in the notational convention, a dark circle will indicate my initial state, okay? Sometimes in automata books, you'll also see this with a little in arrow, okay? Any ring, any sort of ringed state will be a final state. That means you're allowed to stop there, okay? So there may be multiple final states. There's always only one initial state in any of these graphs, okay? Now, reading off this graph, what's a sentence that's permissible by this? The cat meows. Okay. What else? Cat barks, right? Okay, that's fine. How about the dog? Is the dog acceptable? No. Why? There's no double ring here, right? Okay. So partial strings are not accepted, right? Okay. Okay. So as I said, we're labeling on the transitions rather than states, and that's a little bit different. So you'll notice that this has a one-to-one relationship with regular expressions, which you might be familiar with. So this would be the regular expression that corresponds to this would be the or a followed by dog or cat followed by barks or meows, right? Okay, so we're pretty happy about this so far. Okay, so now here's the quiz. Figure out what's going on. What strings are allowed in A but not in B? The cat barks. Yeah. So there's actually, I think, 4, right? 4 different ones, right? Now, why are they, these look superficially the same, right? Okay. But what's going on here? We've split this into 2 things, because we know that dogs only bark and cats meow, right? Maybe cats bark, I don't know. But, so we've split the state into 2, okay? What is the state really encoding? It's encoding the fact that I've seen something when I come into this point. Dog, exactly right. All right. These are not hard questions, right? So the idea is that states in a finite state machine can actually have meaning, and they encode certain things. And usually they encode contextual meaning, right? That I saw a dog coming into this point, right? Now I know that barks is allowable, right? Ran might also be, right? For example, the cat ran or the cat meows, right? So this encodes the fact that I have seen cat at this point, right? Are we happy so far? Okay. All right. Okay, so those were automata. That's my quick sort of intro to automata. We'll get into a little more later, but let me give you the other side of things, which is the transducer. So an automaton, we said, was a constraint on language. It basically says we accept this language, right? You can also use it as a generator if I walk down those paths randomly, right? Now I might want a system that might turn, for example, digits into spoken numbers, okay? So if I am going to have to use this because I'm not that tall. Okay, so if I see the word 1, if I see the digit 1, and that was my only digit, then I'm going to put out the word 1, right? Here's 2, 3, and you can go all the way up to 9. Okay, so now let's follow this path down here. Maybe I see a 1 followed by a 0. I'm going to want to put out the word 10, right? Okay. This is very important for things like speech synthesis, right? Where you've got in digit strings, the synthesizer you don't want it to pronounce 1, 0. You want it to say 10 if it sees 1, 0, right? Okay. So here's one problem that you see. Well, maybe I don't want to actually output anything at this point, right? So we have to have these little epsilon symbols, okay? They were really annoying if you were ever involved in an automaton class and you kind of said, what's the point of an epsilon symbol? Well, they are actually crucial when you have sequences of mismatched length in a transducer. Okay. So what is the meaning of this state at this point? It starts with 1, but I'm also expecting to see something else, right? So at this point, you know, now, here's the interesting question. If this is you'll notice is a non-deterministic automaton, right? Non-deterministic means, how many of you know non-determinism? Some, okay. Non-deterministic basically means if you get one input in, you don't know which way to go. So you have to go down all of the possible paths, right? And this is actually the same as the search problem in ASR. Okay, so you're starting off, now if I just see the input 1, right? Am I in trouble because I have 2 arcs here? Why am I not in trouble? Because I could end up here, right? So is it going to just ignore the input? If I just see the symbol 1, that's my input. Nothing else. No, because this is not a terminal state, a final state, right? Okay, so final state, you have to remember you're never accepting partial strings. So we're using the fact that you have to see 2 symbols before you can put out 10, okay? And we can hook in 20, 30, and you can do this, and I make my students suffer through making digits up to 4,000, or you know, that in the thousands. Okay. So what does this have to do with ASR? Well, it turns out that you can think about the ASR problem using these finite state graphs. Okay, so remember that automata are constraints on languages, and that will actually be, in this case, a language model. And a transformation between units, those are our transducers. And so what we might have is a pronunciation model that says, I see a k followed by an a followed by a t. I'm going to put out the word cat. The same way that I have a 1 and a 0, I'm going to put out the word 10. Right? Okay. Now we can also think of the acoustic model as a transformation from low-level feature vectors into these k and a and all those types of symbols, right? Now it turns out in practice you wouldn't actually want to do that because trying to model a continuous space using a finite state transducer, you know, it's not, transducers are really, you know, finite state things are really good for discrete symbol things. So at some point you actually have another model that actually evaluates Gaussians and basically puts these things as weights, okay? So we're going to talk about weights in a little bit. All right. Okay. Oh, and right. The last thing I should say is that what we're going to do is take a bunch of graphs, put them together, and we're going to what's called compose them, and then search over that graph, okay, and find best paths through that graph. So this now becomes a graph searching problem. Okay. And so now you're saying, well, I don't really care about ASR, right? Why should I even pay attention to all this stuff? It turns out that these tools are pretty generic and pretty useful for a wide range of things. So for example, text normalization, like I was talking about. So 2008, you might want to take the string 2008, comes out 2008. You can do parsing with it. So you can look for expressions like, we did this in the Bell Labs DARPA Communicator project where we're doing travel reservations. So we looked for particular finite state strings like fly from New York to Atlanta next Friday. We say, New York, that's a good city, right? But we do this non-deterministically. So New York might also turn out to be an airport. And then once we have a city, we can parse it in from and city, get parsed into from city, and we get a bottom-up, what we call a bottom-up island parser that way, by recursive application of finite state rules. Okay. You can also do other things like named entity recognition. So you might want to say, this is a name, this is a name, and this is a place, right? And you can do that by looking at the environment that it occurs in, and also some other features, like the fact that Barack Obama is likely to be a named entity because it's probably in your list. Okay. So there's a lot of toolkits out there to do this kind of stuff. The ones that you'll be playing with on Thursday? Thursday, yeah, is the AT&T Finite State Toolkit. And it was sort of one of the main weighted finite state toolkits that were out there. All the people who were there, which includes Richard Sproat, who will be here on Thursday, are really almost all of them are no longer at AT&T. There's one exception, I believe. They're now at Google and NYU, and Richard's at Illinois, and sorry, what? Penn, right, exactly. And so this was not an was not an open source project. So some of the main players in that are actually making an open source version of this, which is called OpenFST. And I've started playing with that, and it's quite nice because you can fold these things into, you can fold this technology into your own application. So we actually use this as a back-end decoder for some of our speech recognition stuff. For a long time, there's been, you'll see a lot of computational morphology and phonology using the Xerox PARC toolkit. That one, I believe, is not a weighted. It's just a general transducer toolkit, but not weighted. MIT runs an ASR lab, and they have an FST toolkit as well. Jason Eisner, I think, had a toolkit here. I don't know if he's actively developing it at the moment. There's a number of other ones. I think there's one in Aachen. And if you do a Google search, you can find several of these. So these are some of the best known ones. Okay. And if you learn the concepts in one of these things, in one of these toolkits, then they're pretty similar across the realm. So you can go pretty seamlessly from one to another. Okay. The exception being that not all of them handle automata with weights, which is really crucial for the ASR. Okay. Okay, so let's talk about what do you do with an FSM, because putting the language out itself is not, it's in itself interesting, right? But it's what you can do with them that really gives you the power. So the first couple things we'll talk about is how do you combine them? And so the main things I'll talk about is union, concatenation, and closure. Okay. And then how do you make two finite state machines interact with each other? So that's what I call filtering. So intersecting, composing, and then I guess self-operations like determinization, minimization, and epsilon removal. And then we'll talk a little bit about best path searching. Okay. Any questions so far? This is pretty low level. You're still being too quiet. Okay. I might have to come out there with a stick. All right. So union. Okay. Boring definition. If A and B are finite state automaton and X is a string, then X is accepted by A union B if X is accepted by A or X is accepted by B. Okay. This is pretty standard stuff. So because I have a 1-year-old, we have a lot of Mary had a little lamb, hickory dickory dock, 3 blind mice going on, right? And we might have any of those stories told. So the union of them is basically combining all 3 of these together. Now, you might ask, this example comes off of what happens when you do a union of these 3 things in the AT&T finite state toolkit, actually. You might say, why do I have an epsilon transition here, an epsilon transition here, but not here? Anybody have a guess as to what? I mean, basically, you can see that this either puts out one of these 3 sentences, right? Okay, so this is equivalent as if I had removed these epsilons, right? Why do you think they put the epsilons in there? It's a very practical software engineering answer, not very technical. It makes the algorithm very easy.
And your examples are particularly easy in that for Mary, Hickory, and Tree, all the zero states, they all have only one outgoing arc. But I could imagine they could have a million.
Right.
And then if you wanted to do it without epsilon, the zero state of the new thing would have 3 million arcs going out.
Right.
Which might be more work.
Right. Well, so if you think about it, when I get to this point, so yes, right, that's exactly the point, is that if I wanted to remove this epsilon, right, what I would have to do is basically merge these two things. I would need to copy all of the arcs coming out of this and hang them off of here, right? That's a pretty expensive operation if there's 3 million arcs coming out. Same deal here, right? Here, the algorithm becomes very simple. I only have to, I take my first one as the lead, and I link in using an epsilon transition, an epsilon from the initial state of here to the initial state of there. Okay, so it becomes it's linear in the number of things that you're unioning, essentially, right? Instead of having to worry about the number of arcs coming out. So there are nice little tricks that you'll see. And I only point this out because if you start playing around with these toolkits, you go, why did it do that, right? There's often a good practical reason why these things come out that way. There's often a completely impractical reason, which was that's the way the guy wanted to code it, right? But some of these things actually have some of these weird artifacts have good software engineering ideas behind them. And we can get rid of these too, actually, if we need to. Okay. So, so that was union. Concatenation basically is if you have x accepted by FSA A and y accepted by FSA B, then xy is accepted by AB, right? Okay. So now I have a little noun phrase and a little verb acceptor, right? Okay, so I've got 9 different noun phrases, I guess, and 3 different verbs. So now, if I concatenate those, right, you get the cat sat on my schnauzer, right? Or any of a number of possible sentences, right? So you can take the same noun phrases and stick them together, right? So that's a nice feature is that if I have one thing that does a repeated function, I can glue them together very nicely. I don't have to build this graph, okay? So you might notice the same use of epsilon transitions, right? What do you think the algorithm for concatenation might be? Is an epsilon arc from where to where? From all of the final states in the first thing to the initial state in the second one, right? Okay, again, it's a very simple algorithm. Okay, but the language people, we don't like the fact that there are these epsilons here, right? So let's get rid of them. And in fact, there's a tool in most of the toolkits that calls for epsilon removal, okay? In this case, it's just as simple as merging states 2 and 3 and 6 and 7. And you can see that we make a slightly more compact version of this. Okay. Epsilon removal always works, I think, for automaton. I believe it does not always work for transducers. Sanjeev is nodding, so I can say that now with impunity. Part of the problem is that with a transducer, you might have a symbol on the input and an epsilon on the output, and you just can't delete that, right? So epsilon goes to epsilons usually can be deleted. Okay. So finally, sort of self-attachment is closure. So you've got A star these are the Kleene closures. So this is Kleene star, which is that you have A repeated 0 more times. A plus A is repeated 1 more times. So here's A union B, or A or B, right? So A or B plus basically goes A back to 0, B back to 0. So you just have an arc from every final state back to its own initial state, right? So it's like concatenating itself to, concatenating it to itself. The other option is star, which basically says that you can accept 0 of them, right? So what they do is they take the plus version of that and add in a little extra star, an extra null state that can be final. So it's dark because it's initial, but it's also final, right? So you can accept 0 of them. Okay. So why would it not be right to just put more A's here instead of putting this back, right, and put more B's here? That's right, that's right. And that's one thing that I notice people when they're writing is that language is would be A star union B star, right? Which is different than A, right, union B star, right? So be careful of the ordering of operations, right? That's one thing to be aware of when you're doing these things. Okay. Okay. So at this point, we figured out how to glue things together. Now let's figure out how to match things up. And that's basically, we'll start with intersection. The idea behind intersection is that we want, if X is a string and A and B are finite state automatons, then X is going to be accepted by the intersection of A and B if it's accepted by both. Okay, so this is like instead of having the or, we have the and, right? Okay. Now, this is actually important because a lot of these toolkits don't actually provide a way to say, is this a member of my language, right? The way you say that is you create an FSA which basically contains the string that you're interested in, and then you intersect it with the thing you're trying to test against. Okay. All right. So let's make it a little more interesting to show, instead of having a single path, let's take a transducer that takes all the even numbers up to 12, right? Or sorry, an acceptor. Even numbers up to 12, right? Here is another acceptor that does the multiples of 3, right? If you intersect, what do you get? Get the multiples of 6, which are both the even numbers that are multiples of 3, right? So any path that appears in both of these appears in the answer, right? So it's not just one path, right? It's all of the paths that appear in both. That makes sense? People happy? Okay. Here's a little more complicated thing to see how it works in something that's approaching more the ASR problem. Okay, so I've got these two weird languages, and remember that languages are constraints, right? So I'm not going to write, what I want is to, if I want to talk about this constraint has to be possible and this constraint has to be possible, I'm going to intersect them, right? So here's one language. I have to have at least one A, optionally followed by a number of B's, exactly one C, exactly one D, and then at least one E. Okay. So that's one language, and that's my base language. And now I'm going to put another constraint on top of it, which is if vowels appear, they have to appear at least twice. I'm not saying that they have to appear. I'm just saying if they appear, they have to appear at least twice. Consonants, we are permitted, and they happen at least once. So we're not going to put any constraints on this, right? Now, if I left out that consonant bit, which is something that people do, people might say, oh, right, I need to make sure that vowels happen at least twice, right? They leave out the consonants. Bad things will happen, and I'll essentially, if I left this out, right, and I try to intersect with this, right, if I left the consonants out of this, what's going to happen? You're going to end up with nothing, right? Because there's no path that does not have a consonant over here, right? Okay, so that's another thing, is that you're often focused on trying to get constraints that deal with some subpart of the language. But you have to remember to put in all the constraints for the parts of the language that you're, in that constraint you have to basically list out, oh, okay, and I'm not putting any constraint on the other parts of the language. Okay. Okay, so now we can intersect these two. And I've labeled the states down here with the combined states that you would follow through the path on. So you start in both cases in 0, right? So the initial state is going to be labeled 0, 0. Okay. Now, I can take an A out of here, and I can take an A out of there. Where might I end up? 0, 1. Or I might end up in 1, 1, right? Because I could end up here. Now, it'll turn out that 1, 1 is a dead path, right? Because I can, from this state 1, I can only see a B or a C. From this state 1, I can only see an A. So that's a dead path. Okay, so that doesn't show up in the final thing. You could, in fact, when you do the algorithm, you do actually build this state as you're doing the intersection, but then you do a reachability analysis at the end and say, oh, I can't get anywhere from here, so I'm just going to get rid of that path. Okay. Okay, from 0, 1, I can see an A and remain in 0, 1, right? Or go back to 0, 0. Or go on to 1, 0, right? So you'd be in state 1 and state 0 over here. That makes sense? Okay, and you can follow that logic through and do all the paths, right? And that's what you end up with. Okay? Everybody happy with that? This is the idea of following paths in two machines in once is a critical thing, because that's what's going to happen when we get to the transducers as well. Okay. All right. So that's what we end up with. Now, that's kind of messy, right? It's non-deterministic. We don't like non-deterministic things. We like to make things deterministic if possible, and we like to make them as small as possible. So there are two operations which I'm not going to go into too much about, but just to mention, where you can take an automaton and create a deterministic version of it, and then also compact it. Okay. So here we're going to boil this part of the transducer down into here, right? Which basically says, 2 A's followed by any number of A's, right? An optional B is optional because you could go off to here, right? Followed by 1 C, followed by 1 D, E, and then any number of E's, okay? This is actually the more readable. So one thing that happens when you do this, you often, not always, often end up with something, at least for small grammars, that's more readable and intuitive when you think about the constraints. Because this is kind of messy. If you were trying to think about like, oh, yeah, at least 2 A's followed by an optional B, C, D, and then at least two E's, right? That's kind of hard to read off of here, but that's a little more easy to read off of here, okay? We like to think in minimal terms, right? We like to think about the minimal constraints that make things happen. Okay, happy? More nods, that's good. No voices yet, but all right. Okay, composition. It's basically intersection on steroids, okay? So you've got transducers which have these input and output symbols, right? And you want to match up two transducers the same way that you matched up two automaton. The automaton, you basically compare the symbols, right? What you're going to do is take the output symbols from the first transducer and match them up with the input symbols. Sort of like, I like to think of it as like matching up DNA sequences, and when they merge together like that, there's sort of like this middle ground. What we're going to end up with, though, is we're going to lose that middle layer. Now, there are implementations that actually keep that around, but the idea is that if you have X going to Y modeled by one finite state transducer and Y going to Z modeled by another one, then the composition of the two will give you something that will take your X's and transform them into Z's. Okay. Why is this useful? Well, maybe your X's are your acoustics, your Y's are your phones, and your Z's are your words. Now all of a sudden I have something that matches my acoustics up to my words, which is what I wanted in the first place. Okay. So we say that you can say A is composed with B. That's how you read that little circle symbol. Okay. Now, how do automata get into the mix? Well, it turns out that any automaton is basically a transducer that accepts itself, right? So if you have a finite state automata A that accepts X, you can also call it a finite state transducer that transforms X into X. Okay, the identity transducer. Then you basically just apply the rules of composition. Okay, so this is a leftover from when I was in New Jersey and driving in New Jersey, and you come up to a stoplight. And so actually this is more the Ohio model, which is yellow goes to slow as opposed to speed up, right? But okay, so you've got green goes to go, yellow goes to slow, red goes to stop, right? If I see these things, so I might have these percepts coming in, right, which are red, green. I'm looking at the traffic light, that's my percept. That's the action I want to do. How do I make my motor control do that? Well, if I want to go, I hit the gas button, right? If I want to stop, I'm going to hit the brakes hard. If I go slow, I'm going to hit the brakes easy, right? Okay, so I compose the two of those, and now I learn, okay, if it's green, I'm going to hit the gas. If it's red, I'm going to hit the brakes hard. If it's yellow, I'm going to hit the brakes easy, right? So that's the composition of those two. Everybody happy? Yeah? Okay, so really it's all about transforming one set of symbols into another set of symbols. That's all we're really doing, and that's what this technique does generically. And then we can put that to use in a lot of different language technology applications. Okay, so here's a little example going back, I think, to your question about, do people use grammars? And this is exactly, if you've got a limited domain task, you might want to use this type of technology because you can specify particular grammar. So, for example, if you're in a less benighted part of the country, apart from Baltimore, where area codes are mandatory, right? Area codes are optional, and then you might have a prefix and a suffix, right? But underlyingly, they all have digits, right? So if imagine an application where I'm trying to get somebody to recognize a telephone number, right? Somebody spoken it in, I need a grammar for that. Okay. Well, With an area code, the prefix is going to be 3 digits, and the rules are they can't start with a 0 or 1, right? Because 0 and 1 are signaling codes to the operator. The suffix is 4 digits. It can start with a 0. That's no problem, right? Okay, so we can write a small grammar for that. A phone number starts with an area code, and so I have a phone number. It's an area code, a prefix, and a suffix, right? Or it can be, a phone number can be a prefix followed by a suffix. Good? Okay, so there's a little bit of optionality in there. Okay, now, how are we going to make that work in terms of getting down into lower level objects? Well, area codes can start with being not 0, 1. We'll use that as a symbol, right? Followed by a digit, followed by a digit. Suffixes are 4 digits in a row. Prefixes, not 0, 1, followed by digit, digit, right? Okay. Now, I could have written out all of those situations by hand, right? But what I really want to reuse is this idea that digit has a specific meaning, right? Or it has a specific thing that it repeats over and over again, right? As does not 0, 1, right? So now if I compose A, it's just my original thing, with B, you can see that basically what I've done is basically stretched out things so that now phone number can be not 0, 1, digit, digit, not 0, 1, digit, 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 right? 7 digits. Or not 0, 1 followed by 6 digits, right? Okay. Everybody see how that transformation happened? Okay. Not magic, but it's just basically, you know, manipulating the symbols. Okay. So what do you think we're going to do next? It's pretty obvious what we're going to do next, right? Is this going to be the end of the road? Well, what my recognizer is going to put out are things like 1, 2, 3, right? What's the next thing that's going to happen? You guys are too quiet. I know you know the answer to this. Come on. Okay, John, you can answer. John's seen the answer already.
Yeah, is that cheating?
That's all right.
Map numbers to words for numbers.
Right. So we're going to map. No. Actually, that's not quite right. We're going to map these symbols, like not 0, 1, to things like digits. Right. Right. Exactly. So there's our next transducer. Right. Now you'll notice that what I've done is created a loop that says I'm not going to talk about any of the constraints from a higher level about the form of phone numbers, right? What I'm going to talk about is the fact that digit can be realized as any one of these things, and not 0, 1 can be realized as any one of those things, okay? And you'll just notice that 0 and 1 are, you know, not on these arcs, right? Okay. So the idea is try and make the machines that you're doing as minimal as possible, so that when you compose them, you don't have you let the constraints interact naturally. Okay, sometimes it's not possible to do that because the intersection will make a state space that it will basically explode. But by and large, it's a good idea if you can pull it off to do this. So now I compose this with my other thing, and now I'm getting something that's looking like a more interesting graph. And this is actually something that you could try and use as your speech recognition graph, like to HTK, for example. Okay. What you might want to do is project to the output symbols because the recognizer might not understand transducers, yada, yada, yada. But, okay. But you can see now we're developing a more and more complex grammar by basically taking these simple things with repeating parts and plugging them in. Okay. Now, this should start to look a lot like context-free grammars as well. And in fact, this is the point that I was making before is exactly apt, is that up to a certain level of composition, if you take a top-level concept like phone number and you keep expanding it, you end up with the same thing that you would end up with a context-free grammar with a limited depth. Okay. All right. So last little bit of mathy goodness. Let me see where we're at. Okay. Is we have these graphs, right? And all I have is symbols on these things. But we know that some graphs are better than other graphs, right? So I'm going to want to have weights. And the weights are going to tell me something about how good one path is over another, because that's going to be exactly what will solve our ASR problem. So what we need is an algebra. And the thing that works very well for this is our semi-rings. So the idea is that you're going to have a set of numbers. You're going to have a plus operator, a times operator, a 0, and a 1. How many of you have ever done like a formal algebra? Okay, not too many. Okay, so this is a pretty new concept. So the easiest one to think about is real numbers. And I'll explain what the 0 and the 1 mean. Right. And I should actually put, people usually put a 0 bar and a 1 bar over here, because just to indicate that it's a concept of 0 rather than the actual symbol 0. Okay. So we have real numbers, and our plus operator will be plus and our times operator will be times. Okay. Okay. The idea is that the semi-ring needs to have various properties. One of them is that the plus operator needs to be commutative, I believe. And there are specialized semi-rings, and most of the ones that we're talking about the same way, is that the times operator also needs to be commutative. The 0 needs to satisfy the property that something plus 0 will always be something. A plus 0 is always A. Okay. A times 0 will always be 0. Okay. And A times 1, whatever your 1 element is, will always be A. So those are the three basic rules. Okay. So that's what we call I call the regular semi-ring. I think it actually has a technical name. Do you know it off the top of your head? The real semi-ring? Okay. So one thing that you can do is, let's imagine taking the real, all the reals, and let's convert everything to log domain. Okay. Take the log of everything. So instead of A, you have log of A. Okay. B, you have log of B. Right? Now, if you take that, then basically you throw in the reals, but you also have to throw in negative infinity and positive infinity into the semi-ring. In particular, positive infinity is really important, because what you want is some representation for the log of 0. The log of 0 is actually negative infinity, and what we're going to do is take the negative of that and make it positive infinity. Why? Well, what we're going to want is something that will be least cost. And so we want the biggest numbers to actually be the smallest. So we take the negative of the log. Okay. So let's ignore this for a minute. When you take A times B, right? If I have plus instead, now if I take log A and log B, the same operation is plus in the log domain, right? So that has and the log of 1 is 0, right? So log A plus 0 is log A, right? Which is the same as saying A times 1 is A, right? So that carries over. So now what happens to the plus operation? Well, the plus operation is a little odd, because there is no analog directly in the log space for adding two things. A plus B does not have a simple operator. But we can call that, we can think of it being a complex operator that we call log plus. And it's going to have the same properties that log plus of 0, log 0, which is in this case going to be plus infinity, will be still give you A, right? Log A, right? Okay. Now, Why is that a good idea? Well, basically, we can talk about representing log probabilities in that space, right? Probabilities are going to be things that go between 0 and 1. And in fact, because of, for reasons that they can actually extend beyond that range because we actually sometimes use unnormalized probabilities in our acoustic modeling. Okay. So why do we want to use that? Well, let's take Dimitri's example that we had in the previous thing. She gave you 3 time steps, right? That probability got to be pretty small pretty quickly, right? Now imagine going out to 300 time steps or 500 time steps, right? You're quickly going to underflow a computer, okay? So if we take the log, that's a space compression, right, in terms of the dynamic range of things. And we can still do the same operators. Instead of multiplying things together, we now add things together, right? The max operation still holds, right? So we can do, so instead of doing times, or, and you know, we do times and plus, we do times and, or times and multiply, we do, essentially or times and max, we do plus and max, I should say, for the Viterbi. Gets a little dicier when you get into the forward probability stuff, but you can handle that. So it still tends to, just as a side note, it still does, even when you go to the log domain, it still tends to underfloat. So you have to do some tricks in the forward-backward calculation to sort of save off little bits of the computation and say, okay, I'm going to rescale everything at this point. Okay. There's a nice paper by Larry Rubiner that sort of indicates some of that, which is, if you want to read up more on what Dimitri was saying, that's also covered in that. The ball and earn model is in there. Okay. Right, so one semi-ring that we find useful, remember I was saying that, you know, we're doing the Viterbi probability that she was talking about. We're doing multiplying a max, right? Well, what if we wanted to just do plus and max? Well, we can make a semi-ring that is plus and, well, in this case, min. Why is it min instead of max? Right, we've inverted the scales. We want to make least cost paths, right? So we're going to look at it, we're going to have a set of operations that basically say, I've got the real numbers plus I've got my positive and negative infinity. My 0 is going to be plus infinity, and my 1 is going to be 0. Okay, so now let's check to make sure that this really does make a semi-ring. Let's do plus first. Okay, so we wanted to say that A plus, sorry, this is times, right? Okay, so A times 0 should be 0, right? So A plus positive infinity is positive infinity, right? And that's my 0, right? So I'm okay there, right? A plus in positive infinity, which in this case my plus operator is min. So the minimum of A and positive infinity is A. Right, okay, good, that works. Last check, we should have A times 1 should be A, right? So A times, which is plus, my 1, 0, gives you A. Okay, so this is a valid semi-ring, okay? Even though it's got this funny min operator in there. But this turns out to basically represent the Viterbi. So that's a nice property. Okay, so now let's think a little bit about weights on graphs. Okay, and I'm going to appeal to roadmaps. That's a nice way to think about these things. So think about states as being points on a map, and we're going to have roads being arcs, right? And those are going to be labeled with weights, which are the distances between the cities. Okay. So what we want to say is questions like, what's the shortest distance between 2 points? What cities are closest to another? So these are all basically shortest path questions, right? So here's a road network, okay? And I want to get from city A down to city H, okay? So how am I going to find that? Well, I could just go, all of these, I've marked this one as an initial state, but all of these are final states. So I need some constraint that basically says, end up in H. Now you're not allowed to talk about, in this world, you're not allowed to talk about the values of the states. You're only allowed to talk about the values of the arcs, right? So we'll do a little trick. What we'll say is, I want a path that is consistent with leaving A, one of the roads leaving A, and one of the roads going into H. Okay? So let me formulate that as a constraint. Show me all the roads that begin with one of these 3 roads. I can take any road I want in the middle, multiple times if I have to. I probably don't want to go back on road 1, 2, or 3, so I'll leave that out, right? Because that will just take me back to A. That doesn't make sense, right? And end up on road 12 or road 13. Okay? You see how so a query now becomes a constraint. Make sense? Right? And what am I going to do with this and this? Expand state 1. Okay. Well, yes, and that was one step in the general algorithm of what finite state operation? Intersection, right? I can intersect these two, right? So you can think about, so intersection really is expanding state 1 following both paths in both constraints. And that's what the intersection algorithm does. And it's just going to, so we can abstract away from the idea of having search individual states by basically saying, give me the paths that constrain, that satisfy both of these constraints, right? So this is the network that results from that. So it's a one-line operation in one of these toolkits. You give them these 2 graphs, you do the stuff. So you don't have to, that's the beauty of it. You don't have to worry about doing all the state expansion. It does this for you, right? So that was exactly the right answer if you weren't working with toolkits, right? Okay, so now I've got all of these paths, and you'll notice I have costs on these things, right? And now I've got a nice initial state, and I've got a nice final state, and I've got all this road network in between, right? And now I'm going to find the shortest path, right? I can use dynamic programming, Dijkstra's algorithm, any of these things, which all basically boil down to the same dynamic programming algorithm Demetria showed, right? Okay, so here's the shortest paths. In this case, taking road 3 directly to road 12 actually give you cost of 70 in this case. Now I printed out the 3 most likely paths in this case because sometimes, especially if you want to do downstream processing where you don't believe in the model that you have here, you might have other models that say, oh, there's road construction on road 3, right? That's not in your original model. Or you might have prosody information you want to bring into your ASR, right? So you might want to get out a graph. You might want to, A, retain this graph, or B, get out an NBest list of possible paths. Okay, so this was something that cost 75, just by looking at the road costs. This was something that cost also 75. Okay, so does that make sense? Everybody see that all I'm doing is searching for. And again, this is a one-line operation. Okay, I'm searching for the best path. Okay, all right. So let's quickly then show how this applies to ASR. Okay. So in ASR, basically what we're trying to do is find the most likely utterance given the acoustic input, right? So we're going to turn the ASR into graph problems. Okay. We're going to make some assumptions, and the assumptions are going to correspond to the different models. Utterances are going to be made up of words, words made up of phones, phones are made up of subphone units, and that we're going to have some way of relating those subphone units to the acoustics. Okay. And what we're going to do is have weighted finite state transducers that talk about how to, the different levels of those finite state transducers. Okay. So quick step through the math just to relate back to Dimitri's slides. Remember, what we're doing is finding the most likely word sequence given the observations. And using Bayes' rule, we can flip this around. And we have a constraint on the language. Ooh, constraint on language. What does that say? Automaton? Right. Okay. And then some intermediate models that talk about the relationships of observations to words. Right? Okay. Constraints on language are automata. Transformations between levels are transducers, right, in this world. Okay. This is the same thing I just said. P of W is going to be the grammar. It's going to be represented by a weighted finite state automaton. You can break down this into various pieces. One is the probability of the observations given the Gaussian distributions, the probability of the distributions given the phones, and so this is essentially the HMM states and the probability of the phones given the words. Okay. Now the weights in this context are going to be these negative log probabilities for the reasons that I was talking about before. It's mostly for scalability, so that you can actually represent the probability of an entire sequence. When you compose, basically you're adding weights of different paths together, right? What does that do? Well, adding weights in the log domain multiplies weights together. So what you're doing is you're multiplying the probabilities together. Okay, so you get exactly the right probabilistic interpretation out. Okay. The best path search is basically now going to be minimum cost, and you can apply any of your favorite minimum cost algorithms. And that's equivalent to finding the most likely path, the highest probability path, right? Okay. So the acoustic models, basically, we talked about this. Every phone is going to be divided into 3 states. And we're going to usually have mixtures of Gaussians. You can also have a number of other statistical models. If you're a weirdo like me, you might use multivariate perceptrons or conditional random fields or. The nice thing is that you can plug in a lot of different ideas to this kind of framework, because what you're doing is separating out the decoding framework from the underlying modeling. Okay. It's nice in abstraction. In theory, you often have to get involved in the nitty-gritty of making things work quite right, but it's a nice abstraction. Okay. So what might the probability of the distributions given them, what probability of observations given the, probability of observations given the Gaussian distributions might look like? Okay. Now remember, what we've got are these 10 millisecond frame observations coming along, these 39-dimensional things. And you can imagine, this is in the abstract, you can imagine that I now have all of the sounds of my language, and I have all of the HMM states, which have their own Gaussian distributions. Okay. So I can score each HMM state, right, by saying what's the likelihood of the data given this HMM state. Take the log of that, take the negative log of that, and that becomes a score. So high is bad, right, in this case. So here's the first state of a, the second state of a, the first state of t, the second state of t, third state of t. I guess this is automatically plotted, so it didn't really care about keeping these things together. We have k, 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 and there's the other t, right? Okay, so in this case, you can see that this actually matches the first state of k pretty well, and the other one's not so well. T is not too bad either, right? So you're keeping alive multiple possibilities at this time frame. This is the second time step, third time step, and you keep on going. Okay? For as long as your utterance is. Okay. Now, the question is, how do you make that into a phone? Well, the HMMs that we typically use can be modeled as a three-state model where you see at least one a, followed by, optionally more, right? First state of a, then you see the second state of a, and you see the third state of a. Okay. We often define this topology for HMMs as well, right? So this is actually, you can read this right off of the HMM topology for most of these systems. Okay. This is the most common topology. So you'll notice that here we chose to model this by converting the first instance of a to the first state of a, the first instance of the first state of a to a, right? We could have done that at the end too. This just makes a slightly prettier model for looking at. Okay, it doesn't really matter, but you'll notice that there's a lot of epsilons involved, right? Because we're going from a really long sequence of different symbols into a single symbol, which is a. All right. Okay. Now, that was just the model for a. I might actually want to have other sounds in my language, right? So I'm going to put in another model for k, another model for n, another model for t. And I'm going to take the union of these, right? And I'm going to take the closure of the union of these, right? Because I want any number of sounds to follow themselves. Now this will also allow a sound to follow itself, which sounds a little odd, but it turns out that it's important for situations where you've got a sound ending one word and a sound beginning the next word. So what we like to call the double S problem. That's important. Okay, so now we have words to phones, which basically say I've got k, a, and t. I'm going to make cat. Okay, same idea. We're taking smaller symbols. We're creating longer span symbols out of them. Dictionary is going to be a composition of all those words, right? And I can take the union of these things. Now, did I actually? Yeah. Okay. Now. So people are happy with this, about you just line up all the pronunciations for each one of these things, right? So now if I take, if I determinize these things, right, I actually get that nice tree structure that Dimitri was talking about, right? Is that all the K's that were here get mapped down into one state, one symbol. And I take the closure of so I take the dictionary and then I take the closure of that. So I'm skating over some extra stuff that you need to do. That if you're really going to get serious with this, you need to do homophones. But the idea is that you imagine you have read and read, right? So like the plant, right, versus reading from a book, right? You can't actually determinize that because they share the same input symbols, right? So you actually have to add some auxiliary symbols to make it all come out nice if you want to do this determinization stuff. Okay. Finally, the automata constraints from the language, right? So the grammars are going to give you the probability of this word sequence, and we can talk about different kinds of grammars. So one is the finite state grammar. Basically just says, these are the sentences that are allowed. The dog barks at midnight, right? Context-free grammars might give you a richer model, right? You can compile those down into context-free grammar or finite state grammars because by and large, you're not allowed to put in an infinite number of words unless you say please, 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 right? But nobody ever says that, right, in real life, except for now. Well, never mind, right? Don't try and do speech recognition on this lecture. But by and large, you can get by compiling down a finite state grammar into, or a context-free grammar into a finite state grammar. Another thing that we talked about a bit was n-gram grammars, and you can approximate them. You can't get them exactly right, but you can approximate them by compiling them into a finite state network. So let me, this is a finite state grammar, right? It allows, sentences like the dog barked at the cat, right? And what we can do is we can add weights to these things to say, my is pretty unlikely relative to the or a, for example. Okay. Or, elephant is less likely in this domain than dog or cat or schnauzer, right? Okay. Now, how do we get at trying to do more large vocabulary type things where we don't want to put these constraints on the language, right? Well, what we can do is create little finite state automata where the states encode the word context in this case. So this is our start symbol, right? And I can transition to word 1 with a probability of word 1 given the start symbol. I can transition from word 1 to word 2, probability of word 2 given word 1, given this probability, and that'll be the weight on this arc, right? So actually, I should have put on this the fact that I have W1 is my output symbol, right? Transitioning into here. This is just encoding the fact that I've seen a W1. Now, one of the things we didn't talk about is what happens if you get a word, something that you've never seen before. So for example, W2 starting a sentence. I've never observed that in my corpus. What language models do is they compute a back-off grammar. Before I get into that, I should say that you could encode trigrams and more bigger language models this way by basically exploding the state space. So at some point, there's a sort of a limited return because you can't fit it into a model with a huge history, right? If you've got 10,000 words in your vocabulary, right? Theoretically, you've got 10,000 squared states in a trigram. That's starting to get, and if you're going for a 4-gram, that's 10,000 cubed. It gets pretty ugly, right? Now, in language models, we don't actually do that anyway. What we do is we have is back-off grammar. So we only specify a certain number of those probabilities, and we back off for the rest of them. So the idea is that we have a way of computing, which I won't go into at the moment, that if I've never seen word 2 following word 1 before, a way of taking the prior probability of seeing word 2 and multiplying by a back-off weight for word 1. So it's sort of a discounting factor. Okay. Now the question is, how does that get encoded over here? Well, what we have is a node called backoff, and you can transition into that node with backoff by emitting an epsilon symbol and putting out the backoff weight, right? Then I can say, oh, and I saw word 2 coming out of the backoff node. So now I have, this would be word 2 goes to the probability, with a weight of probability of this, and that essentially would multiply those two things together, okay? Or in the log domain would add them together, okay? Now, why do I say approximate? Well, this strategy leaves 2 paths for the words, for W1 followed by from the start symbol, right? I could take this one directly, right? Or I could take this path followed by this path, right? Now, if I took this path by this path, right, it probably doesn't matter because I'm just going to throw them all in together, right? And this is probably going to dominate this score. Usually this is a larger score. Sometimes this is not a larger score than this. And that's actually not what was intended. I mean, if you want to say this is there's no way to say this is a really unlikely scenario, right? Because it will follow the backoff path. So there's no good way to do that without making the state space much more complicated. Okay, so that's where this particular idea falls down a little bit. But by and large, we don't have that kind of constraint in play. All right. Okay. So now putting it all together, we've got now all these different models, right? D, H, P, and L, and we're going to compose them, right? So they're going to add together the costs from the different levels, and you get negative log probabilities, in ASR. Now, talking about what Dimitri was talking about, the fact that sometimes we actually do a weighted interpolation of the models. You can actually put in additional operations that say scale the scores on this composition by a certain amount, and that does the same sort of effect. Okay. Now, what happens is that you now can compose the whole thing. You get all of the possibilities in language, but that graph is huge, right? And so we're going to need some tricks to make that more efficient. So just to give you an idea, this is my phone number grammar, right? Composed all the way out down to the down to the distribution level, right? Now, and that was a small grammar, right? So you can tell it's pretty hairy already. Okay, so a couple of tricks. One is determinize and minimize. That basically saves. You want to make things as compact as possible. Pruning is important. So the idea is that you can say, give me a composition of these two things, but stay within 10% of the optimal path or 1% of the optimal path. Okay. The other thing you can do is push the weights, push the costs towards the front. So if you know that you're going to have a bad cost late in the game, but there's only one path to it, it's better to push that towards the beginning so you don't have to evaluate all those states in between. Okay. So there's a whole strategy that's built around that. The other thing I didn't say that's in here, but this was only recently available to people outside the AT&T community, is on-the-fly composition, which is a neat trick where basically you can tell it to compose two models, but it won't actually do it until you try and do things like best path operations. And then it will do the composition on the fly. That saves a lot of space, and it's really crucial for getting real-time systems out of these things. That used to be only available internally to AT&T, but the OpenFST tools now actually do this, which I'm pretty excited about. So that's something I need to put on the slide. So why is this an interesting thing? I use it as a teaching tool. I mean, and so that it's representationally cleaner, and you can see all the parts of the system. And what I have my students do is actually go through and put together parts of the system. And I'll give you links to that tutorial if you're interested. So you can see sort of what are the intermediate stages of this, right? Another thing is that the underlying decoding structure is roughly the same. And the third point that I should have put on there that I didn't is that if you can think about higher level constraints to put into your system, then you can, and where scores are, being multiplied in together, then it's kind of nice because you can take an existing system and then just plug in your model into this composition chain. Okay. So it's nice for trying out some ideas. You may not want to make a full-fledged decoder, but it's nice for research purpose at the very least. I mean, the AT&T decoder actually did use this as its base technology, and I know that you guys did play around with this for a while too. Okay, yeah. So, oh, right, I did say it. Okay, good. Right, easy to add new levels or combine representations. So a lot of stuff that I did and Marat did, Sanjeev's student who was contemporaneous with me, were things like, how do you learn phonological rules? How do you want to learn how pronunciation alternations happen? You can also build more. I give you, just because it's easy to describe, a little thing on using monophones, but actually you can implement triphones with this pretty easily. The other thing that I find useful is that you can use almost anything going into this. So one of our latest things is we're using conditional random fields to propagate scores upwards and then decoding over that. And that seems to work kind of nicely. And if you have downstream of it some other FSM stuff, like when we were at Bell Labs, we were doing this FSM parsing stuff, you can just combine it all together in one clean framework. That said, there's probably a lot of inefficiencies when you do that, so it's not like a silver bullet. But it's a nice thing, a nice mathematical representation to think about things. So getting the efficient model, well, that's really the point, is that getting an efficient model is going to take you a lot of thinking about how to do it right. There's a lot of easy ways to do the dumb thing and make your system run out of memory really quickly. But if you can think about your problem a little bit, you can actually often scale things appropriately. The other thing is that using an FSM, doing any of these longer distance dependencies, it's kind of an expensive thing. So when I was talking about 4 grams, right, it takes n cubed states and naive implementations. So dependency grammars, you might have to approximate or do it not at all, or rescore an FSM, or. So not everything is going to be able to be shoehorned into this idea either. Okay. So last slide. If anybody's interested in learning more about this stuff, I have my old tutorial stuff that I used from my class and from the summer school a couple years ago. And feel free to send me email. Mm-hmm.